Hello and welcome to lesson 5.1 on operations with higher order polynomials. This kicks off unit 5, which is the topic is polynomials. As a quick note, just before I begin this lesson, I am still recovering from my cough. I've gone to the doctor twice. The doctor has still not given me antibodies, says it's just allergies, your lungs sound fine, you'll be okay, just let it pass. It's been about 3 or 4 weeks now, so I don't know. Anyway, just apologizing for any coughing I'm doing during this video. I really want to get these up, so you're just going to have to bear through the coughing. I'm so sorry. If you hate the coughing, go watch Khan Academy or Organic Chemistry Tutor. They're great too, okay? Alrighty, so introduction here. It says, what's a polynomial? Well, a polynomial is an expression of variables and coefficients that are all kind of combined together, linked through addition, subtraction, multiplication. It's important to note, and I'm going to highlight this, it is important to note that the exponents, or what are called the powers of the variable terms, must be positive integer values, meaning whole numbers, right? That's it. Just your exponents on those terms are whole numbers. They're not fractions. They're not negatives. They're just whole number powers, okay? The standard way to write what's called univariate, you'll see that word right there. Univariate just means one variable, right? Think unit, one, variate, variable, right? So the standard way to write a polynomial is to say, okay, it's a sub n, so that's a subscript n. Sorry, I like that. There we go. A sub n times x sub n, x to the power of n. So n is the subscript on a, which is just to kind of denote that it is the coefficient on the variable x to the power of n, okay? That's it. And so they think, okay, what's one exponent less than n, or one number less than n? Well, that would be n minus 1. I'm going to zoom in here. Say a sub n minus 1. And this is x to the n minus 1. You see, because n comes after n minus 1. N minus 1 comes before n, right? So this is the standard way to start writing that. And we're just going to write the powers in decreasing order until, so say dot, 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 all the way down until you hit 0, right? So you say a sub 2 on x squared plus a sub 1 on x, which, if you think about it, it's x to the 1, right? But we don't really need to write the 1, plus a sub 0, or a naught. And notice, I don't write an x there. Oh my gosh, pen. I don't write an x here because it's technically x to the 0, but anything to the power of 0, well, I should say most things to the power of 0, are equal to 1, okay? And so I don't really need to write that x there. And so I just have my standard form here. I'm going to lasso this just because I can. I want to center this a little bit. There it is. And so, yeah, n is what's called the degree of the polynomial, n. So the degree is the highest exponent, so it stops here. And just, you'll notice the exponents are in decreasing order, n minus 1. See, the term that would be right here would be a sub 3 to the x cubed, okay? Anyway, here's some examples. Okay, so what are examples of polynomials? Well, it could be like, let's say 4x cubed minus 2x. There you go, there's an example. How about x squared plus 1/2 x plus 2? There you go, there's another. How about 3? Yeah, that's fine, right? You could have a constant. How about, I don't know, x squared plus 10? How about, I don't know, x to the 7th minus x to the 5th plus x cubed plus x, okay? And you know what, I'll put a 2/3 in front of here. I don't care, right? You'll notice that in all of these examples, the exponents are all whole numbers, right? All of them, whole numbers. Here are some non-examples. So non-examples would be like x to the 1/2, x to the -1, or maybe even worse, x to the 1/2 plus x to the -1. Or, like 2x cubed minus x to the 1/3. That's not a polynomial. Even 4x to the 5th plus 2x squared plus, 3 over x minus 1. That's not a polynomial, right? So the idea is polynomials that are variable terms have whole number exponents. That's it. The coefficients could be anything, although we usually limit our coefficients to rational numbers, but that doesn't mean they have to be. I just want to move these around so they look more aesthetically pleasing. Like this. Come here. Oh, I'm just going to get rid of the 3 because who cares? Let's just do that. Okay, let's say here's x plus 3. There's 10. All right, there you go. So hopefully this conveys the idea of what a polynomial is. Oh, I forgot another one. How about this? 3 to the power of x. There you go. That's not a polynomial. Okay. All right. I've said this word degree, so let's talk about that. The degree of a univariate polynomial is the highest exponent that occurs in that polynomial. So if I go back and just kind of look at these examples, right? The degree of this polynomial that I'm circling is 3. The degree of this polynomial I'm circling is 2. The degree of this polynomial is 7. Keep in mind, you could, there's that cough. You could write these powers in any order, right? Like, it's fine to say that it's like x cubed minus x to the 5th. You can do that. That's fine. But the standard way is to write it in descending order, right? Descending powers. Okay. So that's what's meant by degree. Sometimes you might see this denoted as degree of f of x. If you have, like, what's the degree of a function, it'd be denoted that way, okay? Also, there's a thing called order. So you could kind of use these words interchangeably for now, as long as we're operating in this context. You say, like, okay, because we call them higher order polynomials. That just means higher degree polynomials. It just means more than 2, okay? It just means cubic and so forth, right? So degree, order, same thing, okay? Only thing is, order has a little bit more to it and means more the deeper you get into math, okay? And then, of course, right here, you could just kind of read this too. It says the prefix poly means multiple or many, and so polynomial means multiple terms. Is that nomial just basically means name, right? Nomial basically means name, which is meant by terms, okay? Now, you can see here all this stuff. You probably already know this, right? What's the degree of 0, right? It's x to the 0. It's constant. Maybe I'll even write that next to it, right? This is x to the 0, which, by the way, equals 1. This is x to the 1, which is just x. This is x squared. This is x cubed. This is x to the 4th, x to the 5th, right? So all of that, those correspond with your degrees. And just a little classification here. If you only have one term, it's called a monomial. So, let's suppose you have like 3x, right? And then a binomial would be like 4x plus 1. Let's say 4x squared plus 1. And then a trinomial would be like 5x squared plus x minus 3, right? And then a quadrinomial is going to be like 10x to the 7th plus 10x to the 3rd plus x squared minus 8. I don't know. It doesn't matter. I'm just making things up. And that's just meant by the number of terms, right? 1, 1, 2, 1, 2, 3, and so forth. Okay. Yada, yada, yada. That's boring. Let's go on to addition and multiplication of polynomials, which is also boring. This is just typical stuff. You already know how to do this, okay? Addition, you combine like terms, okay? Like terms are the things with the same variable in terms with the same degree. So x cubed plus x squared, question mark? You can't combine that, right? They're not like terms. Multiplication, you just need to make sure you use the distributive property. Thing is, you're pretty used to just doing distribution of binomials. You've really only done that, right? You've done what's called FOIL, right? First, outer, inner, last. You've done that. Or sometimes you make the box, right? Which, by the way, you can still make a box. But we're going to be working with more terms, so you just have to multiply all of them, okay? So here's the first example kind of worked out. We're just going to multiply these two things. That's it. So if you want, right, you could draw the little arches like this. And you know what? Why not? I'll do it in two different colors. Why not? So in the red, I do x times x squared, right? Here, I'll erase it so you can follow along. X times x squared. Well, that's just x cubed. And then x times 2x. Well, that's just 2x squared. And then x times 4. Well, that's just 4x. Hey, look at that. Amazing. And then I'll do the same thing. Negative 2 distributes here. It's negative 2x squared. Negative 2 distributes to positive 2x. That's negative 4x. Then negative 2 distributes to positive 4. That's negative 2 times 4 is negative 8. Oh my gosh. How lovely. And then from here, I'll just combine like terms, right? So this guy and this guy, those are the same thing, right? They're the opposites, I should say. So 4x and negative 4x cancel. 2x squared and negative 2x squared cancel. What am I left with? I've got x cubed minus 8. Oh, how beautiful. And notice it asks us, can you classify the resulting polynomial? I say, yeah, sure. This would be a cubic binomial. Right? Cubic, because the degree, right? The degree is 3. And it has 2 terms. There you go. Okay, let's work out the next one. By the way, you can multiply in any order. It is totally up to you how you want to multiply these things. So you'll notice I got 4 multiplications here. It's a product of 4 different items. You could multiply these 2 first, or you can multiply these 2 first, or you can multiply these 2 first, whatever you want. It doesn't matter, okay? In fact, I'm going to multiply these 2 together in one step. I'm going to say x distributes to x plus 1. That's x squared plus x. How beautiful. And you know what? In the other one, I'm going to do the multiplication here. X times x, that's x squared. X times 3, that's 3x. And then negative 1x, and then negative 3. Yeah? And I'll just combine my like terms. I got x squared plus x squared plus 2x minus 3. And now we'll distribute these things again, right? X times x squared is x to the power of 4. X times 2x is 2x cubed. X squared times negative 3 is negative 3x squared. X times x squared is x cubed. X times 2x is 2x squared. X times negative 3 is negative 3x. Let's combine our lovely like terms. You see you've got 2x cubed and 1x cubed. Hey, those add to get 3x cubed. That's x to the 4. Sorry. X to the power of 4 plus 3x cubed. And then negative 3x squared plus 2x squared is minus 1x squared. And then there's minus 3x. Hey, look at that. So I noticed that the degree is 4, right? Degree is 4. And there's also 4 terms. So that would classify this as a what, right? Technically, a quartic, because it's degree 4, quadrinomial. Now, real quick, for my sanity, I'm going to double check this because I feel like I didn't do anything wrong, right? I'm just double checking here. X squared. You could scroll along. You could just scroll forward, okay? X times x squared, that's 3x, and that's minus x minus 3. That's that. And then x squared, which is 2x cubed, x squared minus 3x squared, and then x cubed, and then x is 2x squared, and then minus 3x. And then that is good. Yeah, okay, we're fine. I was just double checking my work. I don't want to teach you the wrong thing, okay? All right, let's move on to the next page. Review on factoring. Now look, if you are a master of factoring, you could probably skip the next, I don't know, 15, maybe 20 minutes. I don't even know how long it's going to take me. If you are, you're kind of whisking your hands going, oh, I already know this, Mr. Spake. You can skip forward, okay? Because right now, I'm just going to review factoring. I'm not going to do a full reteach of it, but I'm going to review some problems, okay? To just kind of help support you leading into the next section on factoring. So real quick, as a reminder, we say that something is a factor if it divides evenly into something. Yeah, so A divides evenly into N, right? You say A is a factor of N if A divides evenly into N. The same is true for polynomials. If you have two polynomials, you say let P of X be a polynomial, and let's say Q of X is also a polynomial, then Q of X is called a factor of P of X if they divide each other, right? That means Q of X divides evenly into P of X. Now, a few things to note. It is actually really I wish I hadn't told you to skip forward because this is important. Whoops. Anyway, it says, there's that coughing. The quotient, maybe the quotient is the result of division, right? The quotient of P of X over Q of X is itself a polynomial. This is true. Assuming that Q of X is a factor of P of X, okay? Now, you have to make, this is under this assumption, all right? This is very important, by the way. I'm going to take my time talking about this. This is so important. I'm putting stars next to it. Anytime Mr. Spake puts stars next to something, you should probably memorize it, okay? You should probably, write it under your eyelids so that when you go to bed, you shut your eyes, that's all you see, yeah? You say, I'm going to write under my eyelids that the quotient of P of X over Q of X is itself a polynomial if Q of X is a factor of P of X, yeah? Another thing to note is their degrees, okay? So if you think about the degree of Q of X, well, Q of X goes into P of X. It means it divides evenly in there. It has to be either the same degree or smaller degree. So it's going to be the degree of Q of X is going to be less than or equal to what's called the degree of P of X. This is a really important fact to note. And I know that might not make a whole lot of sense just right off, me just saying it. But I think as you work through this unit and you come back to this principle, you'll really see this sort of outlined, right? Because if you say that, look, I don't know. Here, look, here's a super common one. X squared minus 4. You know this factors is x plus 2x minus 2 is difference of squares, right? That means x plus 2 is a factor of x squared minus 4. And notice the degree. The degree of x plus 2 is 1, but the degree of x squared minus 4 is 2. And so you would say that, the degree of P of X, which is this guy, is greater than the degree of the dividing polynomial, which is this. Yeah? We do specify that it can be equal to because think of it like this. 5 divides evenly into 10, right? Like 10 over 5 is 2. Yay, great. But doesn't 10 also divide itself? Like 10 over 10 equal to 1. So that equal to condition is just the idea that, if it's the same polynomial, then yeah, they're equal. Okay, lastly, the roots of Q, right, which is the divisor one, or is what you're dividing by, the roots of Q of X equals 0 are also roots of P of X equals 0. Now, it's not necessarily true the other way around, right? Again, think about this. If you look at x squared minus 4, what are the two roots? Well, 2 and negative 2. And what were the roots of x plus 2? Well, negative 2. You say, oh, okay, so negative 2 is a root of the dividing thing, right? Which is here. It's present there. But it doesn't work vice versa, right? So anyway, you know that if it's a root of the factor, then it's also a root of the overall polynomial. Okay, and we've used that principle before anyway. Okay, in lesson 4.0, we covered 5 different types of factoring techniques. This is the review you can skip if you're really, really comfortable with it. So we talked about GCF, grouping, trinomials, difference of squares, perfect square trinomials. And so I've got just 5 examples here to kind of review that just really, really quick, okay? It's more so of a classwork thing than it is necessary for this video, but oh, why not? Let's put it in. So the first thing you look for is always GCF. And so I'm going to look at, okay, if I look at my terms here, if I look at 12x squared y squared, well, that's 6 times 2 times x times y, right? And then if I look at 18xy, well, that's 6 times 3 times x times y. And then if I look at negative 36y, that's like negative 1 times 6 times y. And if I think, okay, what do they have in common? Well, they have a y in common, and they have a 6 in common. I'm going to say they have y's in common, and they have a 6 in common. So the GCF is 6y, right? So you say that, okay, and I'll label this, right? I'll say, hey, look, the GCF is 6y. So we're going to factor 6y out of this. Say this is equal to 6y times, and then you just kind of think of it like division, right? 6 times 2 gets you 12, so I put a 2 here. I'm missing that x squared, and it's y squared, so I need y times y, which is that extra y left behind there. And then plus, and then 6 times 3 is 18. I'm missing an x, but I already have a y, right? And then minus 6 times 6 is 36, so that's a 6 there, but I already have a y. Done. Okay? Done. That's GCF. That's just a quick reminder on it. That's all it is. It's just a reminder. If that did not make any sense to you, you probably need to go back to lesson 4.0, okay? Go revisit that and observe. Okay, the next example is over factoring by grouping. So I'm going to change colors here so it doesn't get it's not a red C. Factoring by grouping just means you group the first two, or, well, you don't have to necessarily group the first two, but you group them in such a way that when you factor out GCF, you see a new GCF, if that makes sense. I'm going to zoom in here. So from the first pair, I notice, okay, 14 and 12, the greatest common factor there looks like 2, right? But also in particular, 2x cubed. That's because x cubed goes to x4 and x cubed. And what's left behind would be 7x plus 6, if I'm just factoring out 2x cubed. And then if I look at the GCF of the other one, well, 7 and 6 are called co-prime. They don't share any common factors. But x squared and x, oh, well, I can take out an x. So this would be 7x plus 6 here. I say, oh, look, it's 7x plus 6 and 7x plus 6. That itself is a common term. So it factors out as 7x plus 6. And what's left behind is 2x cubed plus x. And we are done. Right? Oh. Well, I technically... you could go further. Could go further. You say, wait, what do you mean, Mr. Spake? Well, observe that all of these terms, oh my gosh, they all had an x. I probably could have factored that x out. So what I'm saying is, if you look here, this has x cubed, this has an x, there's still a GCF in there. You could actually factor this further as x, and then I have my 7x plus 6, and then my 2x squared plus 1. I could go further, like so. All right, that's actually kind of a spoiler for what we're going to be doing later. It's called multi-step factoring. So anyway, there it is. That's grouping illustrated, okay? You just group terms, look for GCF. Okay, let's look at example 3. So I got factor 9x squared minus 3x minus 2. So this is just a traditional quadratic, right? Standard form quadratic. We just use these little X puzzle things, right? 9 times negative 2 is negative 18. And then negative 3 is down here. So what, 6 and 3? But 6 is negative. And so then this becomes, I wanted to switch colors. Hold on. Sorry, I know I could probably just do that on my own, but like, whatever. I'm just going to do it because I want to. Because Mr. Spake likes to. Okay, there it is. And so I say this is 9x squared, and then I'm splitting this middle term, right? Negative 3x becomes negative 6x plus 3x minus 2. And then I just do GCF, factor by grouping, right? So if I group the first two, and then I group the next two, then I take out GCF as 3x. I get 3x minus 2 here, plus, oh, look, that's 1 times 3x minus 2. So this factors as 3x minus 2 times 3x plus 1. Okay? And there it is. Ta-da! Factor by grouping. Okay. With the quadratic trinomial. Example 4, factor 25x squared minus 36. This is a difference of squares. A squared minus b squared, which is like 5x squared minus 6 squared. So what this factors as, right, is 5x plus 6 times 5x minus 6. Let's call that difference of squares identity, right? And we know that. We've been doing that, yeah? You're going to see difference of squares so many times. So many times. Not just in this class. Just all over the place in math. Just everywhere. It's going to pop up. Okay, last one. And this is the quadratic trinomial. Perfect square trinomial, I mean. So this is 2x squared minus 2 times 2x plus 1 squared. You see, this follows the pattern a squared minus 2ab plus b squared. Do you see that? Because it's 2 times 2x. This is 2x times 1, right? So anyway, this follows a quadratic factoring pattern. This is set equal to a minus b quantity squared, because that's how perfect square trinomials factor. So that means that this whole thing equals 2x plus 1 squared. And there it is. Okay. And I might, I'm going to just lasso those and move them around a little bit. So you come down here. You come right here. I'll take you, put them right. Okay. Well, no, I'll erase all that. Okay, sorry. I know I'm wasting time, but I don't care. I don't care. It's 2x plus 1 squared. There's always that fast forward button. If I'm going too slow for you, you say, Mr. Spake, why are you fooling around? I say, skip. Okay, so that was just review. I'm going to show you some shortcuts now. So just some shortcuts. They're not, I don't know. One of them's kind of a shortcut, but really it's just using your brain and thinking about it. So here's the thing, and I'm hoping you've noticed this by now. When you factor quadratic trinomials, meaning ax squared plus bx plus c, right? If a is 1, when you do that x puzzle, that's it, okay? That's it. You don't have to. I taught you to do factor by grouping because I wanted you to see how it really works. But, if you just look at 12 and negative 7, right? You say, okay, what two numbers multiply get 12, add and get negative 7? 3 and a negative 3 and negative 4, right? Thing is, those are your factors. This factors is x minus 3, x minus 4. And you're done, yeah? You don't have to do that whole grouping thing. You see, grouping over here would suggest that you do x squared minus 7x plus 12, and then you'd say, okay, well, that's x squared minus 3x minus 4x plus 12, so that's x times x minus 3 minus 4 times x minus 3, which is x minus 3 times x minus 4. The thing is, you could just shortcut it to this, which were just these numbers, right? But that only works if a is 1, all right? That only works if a is 1. You can't shortcut it if it's not. And that's the reason I don't teach it the shortcut way at first, because so often when you do a problem like this that's down here, you shortcut it and you're wrong. So careful, okay? Now, I'm about to show you a method I don't approve of. Now, this method irritates Mr. Spake, but it's okay because it's effective, so I'm going to show it to you. This is not genuine math. This is a trick that works, okay? And I can't tell you why it works. So let's factor 2x squared minus 3x minus 20. So I'm going to do the typical puzzle, right? A times c, that's 2 times negative 20, that's negative 40 in the top, and negative 3 on bottom. So what two numbers? Looks like 8 and 5, but 8 is going to be negative, right? So here's the shortcut called the kickback method. This is an alternative to doing grouping, okay? The kickback method suggests you just write it like you did in the first shortcut method, like x minus 8 and x plus 5. But because a is not 1, you're going to take those factors. You're not going to leave it as x minus 8 and x plus 5, because notice, x times x is x squared, not 2x squared. 8 times 5 is negative 40, not negative 20, right? So that's not right. But if you divide it by a, which in this case is 2, then if it divides evenly, you're done. And if it doesn't divide evenly and you're left with a fraction, then you kick it back to the front. And then it's that. And that works every time. Again, this is Mr. Spake's least favorite method. Is it short? Is it effective? Yes. Can I tell you why it works? I have no clue. Okay? I still prefer that you do grouping, but goodness gracious, if you're struggling so hard with grouping, just do this. Okay? This way you at least have a method you can fall back on that works. Okay? And if you're really scared, just always do this method, because then if you just divide by 1, it's the same as the shortcut up here. Okay? Caveat, I'm going to note here. Caveat, you must simplify the fraction. Otherwise, it is wrong. So what I mean by that example, here's an example. Let's suppose you had like x minus, 6 over 3, and then like x minus no, I don't like 3. Let's say like 12 over 6, and then like x minus 3 over 6, well, then that's like x minus 2. But you can't say, you have to make that 3 over 6 a half, and then you can kick it back. So like 2x minus 1. Like you must simplify 3 over 6. Okay? I can't tell you why. I don't like this method. So I'm having an allergic reaction to showing you this. I don't even like it. Okay, whatever. I'm going to move on because that method's stinky. All right. But you're welcome to use it. It's fine. I won't judge you, okay? You can use it. And then lastly, sometimes an effective shortcut is just called guessing and checking, which is how Mr. Spake does it. This is especially fast if A or C are prime. So if your first or last terms are prime, it's so incredibly flat. Oh my gosh, it's so fast. Here's how guess and check works. And it's mostly mental math, okay? So it does require you have some mental ability here. 7 is prime. 5 is prime. So that's 1 times 7, and that's 1 times 5. You got 2 options here. 2 options. You can either say 7x and 1 and 1x and 5, or you can say 7x and 5 and 1x and 1. That's it. And you just guess and check. You say, what do you mean? What are you doing? Okay, look. The first, when you do FOIL, first, outer, inner, last, the first is this guy. The last is this guy. It's the outer and the inner, the OI of FOIL. That's what combines in like terms here, right? So if you just look at the front and end, you can kind of just guess what they are. So you kind of have some things to check, right? You say, okay, well, look, 7 times x, that gives x squared. But if you do 7 times 5, you get 35x. So you're like, oh, okay, this is like 35x and 1x. Whereas the other one, if you do the distribution, is 7x times 1. That's just 7x. And if I draw them a little, 5 times x, or sorry, 5 times 1. I'm sorry, what am I doing? 5 times x is 5x, right? 5x. You see what I'm doing here? I'm doing the OI part of FOIL. Outer, inner, right? So 7 times 5 is 35. 1 times x is 1x. 7 times 1 is 7x. 5 times x is 5x. And if you look at those, you want negative 34x. You want negative 34x. So which of those is going to work? That one, right? 35 and 1. So this leads you take all of this together, and you say, okay, well, it must be the first option. 7x and 1 and x and 5. You say, oh, okay, well, let's see here. What are the signs on this, right? Well, if I want negative 34x, then I want this to be negative 35x, means I want 7 times negative 5 and 7x plus 1. And so that's it. That's how it factors. And so you effectively just did this through guesswork. Now, look, that took me a while to explain. It was probably confusing because this is a skill you develop on your own, okay? I'm just kind of showing you it. You don't develop this through just studying how I do it, right? You do it through experimentation, and then you develop a general number sense, and then you can just get really fast at it. So you'll notice with example 2, this starts to fall apart a little bit because 12 is not prime, and neither is 15. So this method starts to get a little bit messy because you could do 3 times 4 or 6 times 2 or 12 times 1. And then you could do 15 times 1 or 5 times 3. So you have many, 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 many options, right? Many options. Oh my gosh, if you only had 2 before, you have so many now, right? You have like 3x and 1 and 4x and 15, or you have like 6x and 3 and 2x and 5. They say, oh my gosh, so much. But you can still use guess and check to do this. You just kind of have to have some number sense. You just think, okay, look, this number in the middle, pay attention to what that is and think about what your options are, right? If it's really big, then the difference between those outer and inners is going to be really, really big. But if it's smaller, then it's going to be really close together. So look, I'm just going to take a guess. I don't know. Let's just take a guess. Let's take a guess. Let's try 3x and 4x. The question is, you need negative 29x. So think about, okay, well, I could do 5 and 3, or I can do 1 and 15. Well, let's think about that. If you think about 1 and 15, 3 times 15 and 4 times 1, well, that's 45 and 4. I don't know about that. How about 3 and 5 and 4 and 3? 15 and 12? Maybe? How about 3 and 4? 3 and 3, that's 9. Oh, and there you go. There it is. 4 and 5. So if 4 is multiplied with 5 and 3 is multiplied with 3, then I get that 29 there. 3 times 3 is 9. 4 times 5 is 20. If I add this together, I get 29, but I need them both to be subtraction. And there it is. Ta-da. Okay. And so that is guess and check kind of laid out. Now notice, I got lucky here because I picked 3x and 4x at first. I could have picked 6 and 2. I could have picked 12 and 1. What told me that this was going to be it? Nothing. I don't know. It's just innate reasoning, okay? The more you do this work, the better you get at it, the better number sense you develop, okay? If you want to just stick to kickback method, just stick to kickback method. It's fine. Okay. Finally, for the last leg of the video, factoring higher order polynomials. I don't even know how long this is. But surprisingly, I haven't been coughing too much, so I'm kind of proud of myself. So factoring higher order polynomials, this is the last piece of the video. We're just going to talk about how to do it with even bigger polynomial expressions, okay? So these are the newer or extended factoring methods. The first is just called multi-step factoring. Now this one, it's not really a lot for me to teach you. It's just all those methods you did before, you just do any variation of them multiple times. And I'm going to show you that and model that with the first 2 examples here. The next one will be called quadratic factoring patterns. And so this is where you see an expression that it's not quadratic, it's not x squared, but all those patterns you learned for quadratics carry over to those polynomials. And I'll show you that too. And then we'll have a new sum and difference of cubes identity to talk about, which is kind of like the difference of squares, but for cubes. Okay, so let's look at multi-step factoring. The first thing you look for, sorry, I'm yawning. The first thing you look for is GCF. If I look at GCF here, I'll notice that 3, and if this is x to the 5th, that's 5 x's, that's 3 x's. They have 3 in common. So 3x cubed is the GCF. What's left behind? Well, that would be x squared plus 10x plus 25. And oh my gosh, would you know, x squared plus 10x plus 25 is a perfect square trinomial. So it's a perfect, say perfect square trinomial. Oh my goodness. 3x cubed times x plus 5 squared. And we are done. That's it. Look, you can do this whole thing, right? You can do the 25 and 10. You get 5 and 5. And since this is a 1, you can just shortcut it, right? X plus 5 times x plus 5. But I know I used an even quicker shortcut because this itself, this factor, is a perfect square trinomial. This factor is x plus 5 squared. So it was just 2 steps, GCF, and then factoring a trinomial. And I looked at this one. Now, I'll always look for GCF. I'll always look for that. 2, and then that's 1, 12, 4. Oh, it didn't look like anything in common there. And the x's, well, there's no x here. So no GCF. Let's just say no GCF. So I tried the next best thing. I could group. So let's look at grouping. If I group this, I get 2x cubed minus x squared plus negative 12x plus 4. Let's do GCF from there. Well, that has x squared in common, and this is 2x minus 1. And then, let's see, 12x, negative 12x, that looks like they have a 4 in common. In particular, negative 4, so negative 4 times 2x, no. That's supposed to be a 3. I think I had a typo on this. Okay, I'm going to change this on my official notes, but that's supposed to be a 3. Okay? So I'll change this on the printout. I'm so sorry. That is a 3. 3x squared. Or 3x cubed. Because I'm factoring out negative 4. I wanted this to work out. Okay. So let me change this just real quick. I'm so sorry. So incredible. Oh, my heavens. There it is, 3x minus 1. So if I pull out that negative 4, then I get that 3x minus 1. And so this is what's in common now, right? It's 3x minus 1 times x squared minus 4. But now notice, x squared minus 4 is a difference of squares. And so I can say, oh, well, then this is 3x minus 1 times x plus 2, x minus 2. So it's those factoring methods we just talked about earlier, right? It's all that stuff, all the factoring from unit 4 carries over here. And so it's multi-step factoring, right? You took this cubic quadrinomial, you used grouping, and then you weren't done there. You could go even further with the difference of squares identity. And so this is just to kind of model. Multi-step factoring just means keep going until you can't factor anymore. Okay? By the way, you should be able to find the roots of all of this, right? All that knowledge you carried from Unit 4 about finding roots, right? This root is 0. This root is negative 5. That means 0 and negative 5 are the roots of this thing. Okay? All right. Let's look at quadratic factoring patterns. Oh, I like these. I really like these. So here's what a quadratic factoring pattern is. It says it's not quadratic, but it's kind of like it looks like a quadratic, kind of. So here's an example. Suppose that, let's say, look at this. Let u be x squared, okay? If u is x squared, well then u squared is x squared is x to the 4th. So replace this stuff with u. You see, x to the 4th right here is u squared. And minus 29, what did we say x squared was? X squared is u. And then what is 100? Oh, there it is. Now, that looks like a quadratic, right? So the polynomial itself, this guy, well, that's a power of 4, right? That's degree 4. It's not a quadratic, but it kind of looks like one if you use this sort of substitution, right? And so I say, well, okay, let's just do our little factoring puzzle real quick, right? I say, here's 100, here's negative 29. What's that? Negative 25 and negative 4 make that. So then this factors as u minus 25 and u minus 4. But look, you don't want to keep it in terms of u. You want to keep it in terms of x. But this sort of substitution allowed you to factor this. And I can say, okay, well, u is x squared, right? Because that's what we said it was originally. But oh my gosh, notice that. Look, x squared minus 25, x squared minus 4, both of those are difference of squares. That's x plus 5 times x minus 5. And that's x plus 2 and x minus 2. Ah, fantastic. And there it is. Okay? So that's what's meant by a quadratic factoring pattern. Here's another example, example 2. So a kind of dead giveaway to these patterns is you're going to see probably a trinomial. You could see a binomial because, you could do like a, if you get like a u squared minus 9, right? That's a difference of squares. So you could see that. But more often, you'll probably see a trinomial like this. If this power is twice or double the middle term power, then you might try factoring like a quadratic. So let's try that again. Let's let u be not x squared this time, but x cubed. Then that means u squared is x cubed squared. That's just x to the 6th. So you can see, oh, okay, I'm going to make that substitution again, right? X to the 6th is u squared. X cubed is u. Oh my gosh, that's a perfect square trinomial. And if you don't believe me, you can do this. 9 and 6, 3, 3. This factors is u plus 3 squared. But what did we say u was? It's x cubed. So it's x cubed plus 3 squared. And that is the fully factored form of that polynomial. So, by the way, you don't have to write this u substitute. You don't need to write that. I will understand. Honestly, you could just look at this and know it becomes this. You might, okay? I write the u substitution so it becomes a little bit clearer how this is like a quadratic. It's just as a sort of supporting device to illustrate to you how I'm getting from here to here. Okay. Alrighty, last one to talk about is sum and difference of cubes. So this is another identity. So this is just one of those things you memorize. Earlier I said, when I'm just gonna say, hey, you need to memorize this. You need to memorize. I'm not gonna give you this on the test. You have to know it, okay? It will pop up in calculus. Oh, it does. It always pops up when you don't want it to. But as long as you can recognize it, that's good. So, the sum of cubes of identity, look, I'll just kind of show it to you. Here's a plus b times a squared minus ab plus b squared. If you multiply all of this out, a times a is just a cubed, and then that's minus a squared b, and then that's plus ab squared, and then this is plus ba squared, which, by the way, cancels out with the first term, And then this is minus ab squared, which, by the way, this cancels out with this term. And then b times b is b cubed. Hey, look, everything canceled, but I'm left with a cubed plus b cubed. Okay, so this is called an identity, again, because no matter what you put in for a and b, this is always true, no matter what, right? So if you can recognize this pattern, you can always jump from this, which is called the sum of cubes, to this. Now, careful, because if you think about squares, there's a difference of squares. There's not a sum of squares. But for cubes, there is a sum and difference identity. Now, and they're pretty much the same structure, right? AB, a squared, AB, b squared. AB, a squared, AB, b squared. What's different is the signs, right? So this one's positive, negative, positive. This one's negative, positive, positive. You might say, well, how could I remember that, Mr. Spake? That's a lot. SOAP. You say acronym SOAP. I'm going to draw a little bar of soap here. Say, hello. This is my little bar of soap. Say, boop, boop. Soap. And it's got little suds on it. It's got little bubbles. Little bubbles. Soap. You say, what are you talking about? Look at the sign here. If it's sum of cubes is plus, it's same, opposite, always positive. That's what that means. Okay? So if you want to put that here, look at the sign. It's the same, opposite, always positive. Look at the sign. It's the same, opposite, always positive. Okay, I've always remembered SOAP. I love SOAP. It's a great little acronym. Okay, just pay attention to the signs. Okay, so let's use it to factor example. Excuse me. Let's use it to factor example 1. So it says x cubed minus 8. So what's special? Now, hey, just like difference of squares, you need to know your perfect squares. Difference of cubes, you know your perfect cubes. This is x cubed minus 2 cubed. So this is the difference of cubes, so it's going to factor as, sorry, I keep zooming out here, a minus b, that's x minus 2, a squared, that's x squared, then it's plus ab. Notice it's not 2ab. I used to do that all the time. It's not 2ab, it's just ab, 1ab. So it's plus ab, that's 2 times x. And then plus b squared, where b is 2, means that's 4. And there it is. Okay? So maybe what I'll do here to make this a little bit clearer is this is a minus b, a squared plus ab plus b squared, where a equals x and b equals 2. Okay? And that's my identity. It's pretty easy to use as long as you can remember it. It's also very, very easy to recognize because perfect cubes, I'm not going to be throwing 14 cubed at you. So, there's only so many you have to memorize. 27x cubed is 3x cubed, and 125 is 5 cubed, right? So this is a sum of cubes, so it's a cubed plus b cubed, factors as a plus b, so that's same, and then opposite, and then always positive. See, same, opposite, always positive, right? So then 3x cubed plus 5 cubed factors as I'm going to put a little bit more space here. Factors as, well, a is 3x plus b is 5. Now think 3x squared is 9x squared because it's 3x times itself. Minus ab, that's 3x times 5, that's 15x, plus 5 squared is 25. And that is it. Now, a quick note before I move on to the last few practice problems. It's always a linear times a quadratic. It always is, okay? It always factors that way. It's a linear times a quadratic. And that quadratic can never be factored further. Never. Because this pattern right here, a squared minus ab plus b squared, it doesn't factor. That is as factored as it possibly can be, so you really don't need to look at factoring this. Meaning, you don't need to do 9 times 25 and then figure out what two numbers add to get negative 15. It doesn't happen. Just trust me on it. You could try it no matter what. It never happens. Okay, let's finish off this video with 4 practice problems. That's it for the lesson. You're not going to miss anything else if you skip out from here. Man, look at all that beautiful notes. What a great little lesson this is. Maybe it's not little, though. So I'm just going to work through these practice problems in case you need extra, video help here. And I don't know, maybe it helps you. So let's look at 5x cubed minus 5x squared minus 10x. First thing I always look for is GCF. So I say that there is a GCF of 5x. So to take out 5x, and so what's going to be left behind is 1x squared minus 1x minus 2. And then, is that it? No, because x minus 2, right? You can do that. So here's negative 2 and here's negative 1. If you do negative 2 times positive 1, that works. So this is just a quadratic trinomial. It's not a perfect square trinomial. It's just a quadratic trinomial. Factors as x minus 2 times x plus 1. And you see how I'm shortcutting that? Ask yourself, why is Mr. Speaks able to shortcut that again, right? Go all the way back here. A is 1, right? I'm able, when I do this puzzle, I'm able to just shortcut it here because A is 1, because that makes it work, right? X times x is x squared. X times 1 is 1x, then minus 2x is negative x, and negative 2 times 1 is negative 2. Okay. Let's move to the next one. So let's do always GCF first. Let's see if there's anything in common. 27 and 12, those could both be divided by 3, and they both have an x in common. So I'm doing GCF again. Always, I'm telling you, always look for GCF. And then 3x times, this would be 9x squared minus, is that a 4? Because 3x times 4. Cool. And then, oh, hey, look, 9x squared, that's a perfect square, right? Now it's going to be difference of squares factoring pattern. So 9x squared minus 4 is going to factor further as 3x plus 2 and 3x minus 2. Because 9x squared plus minus 4, right? Done. And you see how useful it is to just know the difference of squares identity? See how much time that saves me? As opposed to doing like 9 and negative 4, or sorry, 9 times negative 4 is negative 36. And then saying that that's 0, and then this is negative 6, negative 6. And then having to do grouping, you say 9x squared minus 6x minus 6x minus 4. Oh my gosh, it's exhausting, right? It's just so much more. It's just so much faster to just know the identity. Okay, 2 more. Let's do this one. Hey, look, the second you see a quadrinomial, meaning 4 terms, 1, 2, 3, 4, try grouping, okay? I mean, also look for GCF first, but there's no GCF here. So let's try grouping because it's 4 terms. So if I do grouping, I'm going to get x cubed plus 3x squared, and then plus negative x minus 3. Let's see, they have an x squared in common here, so that's x plus 3. And then minus 1, this is now x plus 3. Okay, cool. So this factors as x plus 3, and then x squared minus 1. Which, hey-ho, howdy, x squared minus 1, that's a difference of squares. I don't know, I'm writing perfect. Difference of squares again. So it's x plus 3 times x plus 1 times x minus 1. And that is fully factored. Beautiful. That's x, let's say that's x plus 3. Nice. Okay, last one. There's my x to the 6th plus 11x cubed plus 24. So yeah, we're going to do a substitution with u here. So this is going to factor like a quadratic. Let's let u be x cubed. Then u squared is x to the 6th. So this is u squared plus 11u plus 24. And you can use a little factoring puzzle like this, 24 and 11. You should get 8 and 3. So you know this factors is oh my god. u plus 8, u plus 3. Getting tired here. But what was x cubed, right? Well, or u was x cubed. So it's x cubed plus 8, and then x cubed plus 3. But notice, okay, so this was a quadratic pattern. And now notice, x cubed plus 8, that's a sum of cubes. Oh my gosh, you're using 2 new things you've learned. So x cubed plus 8, this guy, that's x cubed plus 2 cubed. Right? Here, let me write it like this. X cubed plus 2 cubed. So you got to use the sum of cubes identity. So you know it will factor as x plus 2, same, and then opposite, x squared minus, because it's opposite, ab, that's 2x, and then always positive, plus 2 squared, which is 4. So there's SOAP. And then don't forget your x cubed plus 3 was still there. And so that is the fully factored form. You might be saying, wait, what about x cubed plus 3? Isn't that a sum of cubes? Well, kinda, but not really, because we usually try to stick to integer factorization. We just like to factor with whole numbers, positive or negative, and no cube roots or square roots or anything like that. So there it is. That is some extra practice to kind of hone it in, maybe help you on the homework and all that stuff. So, yeah. Okay. I'd say that was a pretty successful video, albeit with the coughing, not so bad. Alrighty. Well, I hope you enjoyed. I hope it was helpful, and I'll see you around in the next one.